So we're having some fun with fractions today before we continue on with L'Hopital's rule. And if I can, there we go. Okay. The reason I'm doing this in the beginning of class is because, not because I don't think you know how to do fractions, but the fractions in this section do get a little bit more complicated than what we're used to. And I feel like it's been a while since we've like manipulated fractions a lot in class. So what I'm gonna do is maybe go through the first one with you, okay? And then I'll let you be with the last three. All right, so I'm gonna kind of get myself set up here. All right, so whenever we have a bunch of fractions going on at once, like there's a fraction on top and a fraction on bottom, what I like to do is to make one big fraction over another big fraction, okay? And what I mean by this is I have a 2, I have a 1 over x, and I have a big line that says like over, and then 1 over x squared here, okay? This big line here is kind of like the biggest fraction in the whole group, right? That's the biggest fraction that I have, okay? What I want to do is I want to have a fraction on top and a fraction on the bottom, okay? The way I'm going to do that is by multiplying the 2 by the 1 over x. So I have one fraction over another. And if you don't see that yet, multiplying the 2 in here will give me 2 over x over 1 over x squared. Okay. Once we're here, it's very systematic what we can do. Okay. I know some of you can do this in your head, and that's fine. But what I have here is I have one big fraction over another big fraction. Okay. This is where we can work with. Okay. We can work with stuff like this. Okay, so once we're here, keep the top fraction alone. So we're just going to keep this the same. You're going to change the division into multiplication. So we're going to change, and then we're going to flip the other fraction, x squared over 1. Flip. Okay. That's kind of how we go about doing fractions over another fraction. Okay, once we're here, you can multiply across to get 2x squared over x. And then you can kind of simplify by doing x squared divided by x to get 2x. Okay. Any questions on the first fraction? All right. Why don't you try the last 3? To make that a little bit easier, I kind of want you to work in groups of maybe like 2, 3, or 4. And then I'll have, let's see, group this. All right, I know some of you are still working, but I kind of want to go through the rest of them because, well, fractions are kind of like a fraction of what we're doing today. You guys can laugh at that or not, but let's keep going. Let's keep going. All right, so this one looks really scary, right? Has a lot of stuff going on, and you're probably like, how in the world do I do this, right? First of all, I didn't mean for you to use any trig identities here. So if you try to use a trig identity, that's fine, but I really didn't mean for you to do that. So let's just try to simplify the fraction itself and not think about the identities or anything like that. Okay, the way that we do this is we like to write this as one big fraction over another big fraction, right? Now the fraction that I want to focus on is the biggest one, right? I want to put a fraction on top of that yellow line that I just highlighted and a fraction on the bottom of the yellow line, right? Well, I can do that by just multiplying through on the top, right? I can multiply the 4 and the cosine 4x to make one big fraction up top. So this becomes 4 cosine of 4x over 1 plus sine of 4x. Okay. Now this is still over something, right? So let me just highlight the big fraction that came from the last step. Okay. Secant squared isn't a fraction, and I'm not going to use a trig identity because I feel like that just makes things more complicated. But isn't secant squared just secant squared over 1, right? I can do that, right? Okay. Now I have one big fraction over another big fraction. I can do the keep, change, flip thing again, right? So I can keep the first fraction the same. So I know it's a lot of writing. I can change the highlighted division sign into a multiplication sign, and then you just flip the other one on itself. 1 over secant squared x. Okay. Now that we have this, just multiply through. This is 4 cosine of 4x over 1 plus sine of 4x times secant squared of x. Okay, so that's all we're doing in L'Hopital's rule. Okay, we're just changing one fraction into a fraction over fraction, and then keep change flip brings us to a one big fraction. Okay, any questions on this one? Okay, I know it looks scary. We actually will see this exact fraction in our notes in L'Hopital's rule, so we'll come back to this. All right, I think some of us are still writing this down. Alrighty, let's flip to the next page here. We have 1 over x over negative x to the negative 2. Here we have negative exponents, and I feel like that just messes with everyone's brain a lot. But why don't we do the same thing? Why don't we make this one fraction over another fraction? This is kind of like the biggest fraction sign in the bunch. So why don't we change the top into a fraction, which it already is, right? And then change the bottom into a fraction, right? So this is my big fraction sign. How do I change negative x to the negative 2 into a fraction?
X over 1 over x. X squared.
Perfect. Yep, a negative exponent means we just bring it in the denominator. Now I know it's weird because it looks like the negative is like in the denominator of the denominator, but we don't care about the yellow division sign. We care about what's happening on the bottom, right? Okay. So we can do keep change flip again. Keep the first one the same. Change the yellow division sign into a multiplication sign, and then flip the other one in half. So we have negative x squared over 1. Okay. Once we're here, multiplying through, we get negative x squared over x. Okay. And we can actually simplify this. What does this turn into? Negative x, right? If you don't see that, the x here is x to the first power. So when you divide things with the same base, you subtract the exponents, right? All right. Any questions here? All right, let's move on to the very last one with the negative and fractional exponents, which I think just scares everyone, right? Okay, we can still change these into a fraction over a fraction. The biggest fraction symbol is this one in the middle, right? Okay, so why don't we make one fraction above and one fraction below? Okay, how do I change a half times x to the negative 1/2 into a fraction?
Turn the x to negative 1/2 into a fraction and multiply it.
Yeah, good. So let's do that step by step. Good. So x to the negative 1/2 is 1 over x to the 1/2, right? So just changing the negative sign into a positive sign, but you flip it over. Okay. Let's just keep the bottom the same. Okay. And like John said, let's just multiply through. So this becomes 1 over 2x to the 1/2 over 1 over x. Okay. Once we're here, we can do keep change flip because I have a fraction over another fraction, right? So we can do 1 over 2x to the 1/2, keeping that the same, changing the division sign into a multiplication sign, and then let's flip over the 1 over x into x over 1. Okay. Once we're here, just multiply through again, x over 2x to the 1/2. Okay, and I mean, some of you left it like this, but we actually can simplify this a little bit further. What does this simplify into?
X over 2.
Good, square root of x over 2. I'm going to do x to the 1/2 over 2, right? This is x to the first power over x to the 1/2 power. When the bases are the same, we subtract the exponents when there's division, right? And let me keep the 2 there. Okay. Oh my God. I didn't. I don't know what I just drew there. I don't know what just happened. X to the 1/2 over 2. Sorry. There we go. All right. Now x to the 1/2 is the square root of x over 2. And let me just hand this in. All righty. So this would be my final answer. Do we feel a little bit more comfortable with fractions now? I feel like we just haven't done them for a while, and I feel like when we get to L'Hopital's rule, we want to focus on the rule itself and not the algebra with it. So I think it's good that we did this a little bit. All right. Let's go back to our notes from last time then. All right. Does anyone need the notes from last class? All righty. Oh, yeah. Here it is. All right, we're taking out the notes for L'Hopital's rule. Let me just show you what they look like. All right. Oh, not this one. Yeah, so we're taking out these notes on indeterminate forms and L'Hopital's rule. Okay. Now, so far, we've talked about a bunch of different things. Oh, do you need the Okay. Yes. All right. So far, we've talked about indeterminate forms. We've talked about, I think, 3 of them, right? We've talked about 0 over 0, infinity over infinity, and 0 times infinity. Those are the 3 ones that we know how to do, okay? When we have a 0 over 0 or infinity over infinity type limit, what we do is we take the derivative of the top, the derivative of the bottom, and then that becomes our new limit, okay? That's basically what L'Hopital's rule says, okay? So we did a couple examples with the 0 over 0 and the infinity over infinity, but we haven't, we started talking about what happens when we have a 0 times infinity type limit, okay? Whenever this happens, it's another indeterminate form. And we said that the way that we are able to do these is to first change the equation into a 0 over 0 or infinity over infinity type limit. So change the product into a fraction somehow, okay? This is either done by changing the, like using exponent rules to change like x into 1 over x, or use trig identities, which we haven't talked about yet, okay? So that's kind of where we left off. Let's do another example and see what happens. All right, let me get off this example here. All right, we're going to start talking about what happens when we see trig in our L'Hopital's rule. Let's talk about what happens here. Okay. Let's see. We have natural log of x times tangent of x, and we want to see the limit as we go to 0 from the right. I told you before that the left and right doesn't really matter with L'Hopital's rule, so it doesn't change how we do the limit or anything. Okay. The first thing we do is we plug in, right? So we plug in, plugging 0 into our function gives us the natural log of 0 times tangent of 0. Okay, and remember, we're going from the right-hand side of our graphs, okay? What does natural log approach as we go to 0? Negative infinity, right? So that's definitely negative infinity. What does tangent approach as we go towards 0? Think about the graph of tangent. Kind of looks like the Disco Man, but a little bit squeezed in. 0, right? That tangent of 0 is literally 0, right? So that definitely goes to 0. Okay, because we have a negative infinity times 0 type limit, this is an indeterminate form, okay? So that means we can use L'Hopital's rule, but L'Hopital's rule doesn't work with products, okay? When we have a product, we have to change it into a fraction somehow, okay? When we have polynomials, it's pretty easy. Like you just kind of do the 1 over trick. But when we have trig functions, it gets a little bit more complicated, okay? Natural log, I'm just going to tell you upright, there's no way to make natural log into a fraction unless you do like 1 over the natural log, and that won't really help you. Is there a way to change tangent into a fraction?
Yes.
How do we do that?
Sin x over cosine.
You do sine x over cosine x. I'll tell you, if you try that, you might get a little confused. Is there another way?
1 over.
Yeah, right. Tangent is related to cotangent in a way that tangent is 1 over cotangent of x, right? We know that those two are related in that way. Okay. So another way to write this limit is the limit as x goes to 0 plus of the natural log of x over cotangent x. Okay. The reason I didn't do sine over cosine is because if I want to do L'Hopital's rule, it might actually haven't figured out if it works or not. But you'd also have to use the product rule, and that would be a lot. So let's do cotangent. Seems a little bit easier. Okay. So all we did is change the function into a fraction. That's all we did. Let's plug in and see if we can use L'Hopital's rule. Okay, so next we're going to plug in. Okay, we have the natural log of 0 from the right again, and the cotangent of 0. Let's see where that goes. We already said that the natural log of 0 goes to negative infinity. Okay. What does the cotangent of 0 go to? Well, we said tangent goes to 0. Cotangent is 1 over tangent, so it's going to whatever 1 over 0, which is infinity. Yeah, so 1 over 0 is going to infinity, so cotangent has to go to infinity. Okay, because we have an infinity over infinity type limit, this is an indeterminate form, we can use L'Hopital's rule. Okay, so let's go ahead and do that. L'Hopital's rule. I'm just going to use my equal sign with the LH on top just to be like, hey, I'm using L'Hopital's rule. Okay. L'Hopital's rule tells us that I can take the derivative on top and the derivative on the bottom. What's the derivative of ln of x? 1 over x, good. What's the derivative of cotangent of x? Something, yes. It's definitely something. Again, hint has a negative.
Negative tangent x.
Not quite.
Squared.
I think I heard it cosecant squared, right? The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. Okay. All right. Thinking back all the way over to test 2. All right. Let's keep going. We need to clean this up a little bit. We have a bunch of stuff going on. Now, let's just think about how to make this easier. I have a cosecant here. Cosecant is going to be kind of hard if I want to plug stuff in. So maybe at this point, I should change stuff into terms of sine and cosine. Okay. So once I'm here, is there a way I can represent cosecant of x or cosecant squared in terms of sine or cosine or tangent?
You give me sine.
Give me 1 over sine, right? So using a trig identity here, I know that cosecant squared is 1 over sine squared. Okay. Another reason I did this is because I want to make this a fraction over another fraction. A way to represent cosecant as a fraction is to put it over sine, right? So that's a good place to go. All right, let's keep going. I have a fraction over another fraction, which means maybe I can do the keep, change, flip thing, right? So this is the same as the limit as x goes to 0 from the right. I'm going to keep the top the same, change the division into multiplication, and then flip the other one. So this becomes negative sine squared x over x. Oh, sorry, not over x, over 1. Doop. So everyone see how I got there? Good. Let me just clean this up real quick. We are going to 0 from the right, multiplying through, we got negative sine squared of x over x. Okay. All right, once we're here, we can try plugging in again and see if we get an answer, right? So let's plug in. Okay, we have negative sine squared of 0 over 0. What's the sine of 0? 0, right? So sine squared would also be 0. Looks like we have another indeterminate form, right? So this is another indeterminate form. What does that mean we have to do? Again, we got to do L'Hopital's rule again, okay? So let me just write this out. Have to do L'Hopital's rule again. And L'Hopital's rule involves taking the derivative of the top and the derivative of the bottom. Looking at the top, I think we're gonna have to think a little bit hard about how to take the derivative of the top there. What rule do you think I'm gonna have to use to find the derivative of negative sine squared of x? Chain rule, right? So chain rule. What's the outside function? Something squared, right? And the inside is definitely sine, right? Because we're squaring sine, right? Now, technically, the outside is negative something squared, right? Okay. So using the chain rule, taking the derivative of the outside is going to be negative 2 box to the first power. What's the derivative of the inside or sine? Cosine, good. Okay, now we can stick the inside back in here. Okay, the derivative of negative sine squared x is negative 2 sine cosine. All right, so let's use L'Hopital's rule again. And this is the limit as x goes to 0 from the right of, well, the derivative of the top, which we just found, negative 2 sine x cosine x. What's the derivative of the bottom? 1, good. Okay, so this is the limit as x goes to 0 of negative 2 sine x cosine x. I guess we can plug in now, right? We got negative 2 sine 0 cosine 0. Okay, what's sine of 0? 0. What's cosine 0? 1, good. Is this an indeterminate form? No, right? The only one that we know is 0 times infinity. So this one actually is not an indeterminate form. We can literally just multiply the numbers together and we get 0. Okay, so we did all that work to figure out that the limit is 0. All right. Any questions on example 9? All right, I know this one was really long. It's probably not something I would ask you on a test or quiz because I feel like this one was kind of complicated. But it is a good example of showing how to use L'Hopital's rule twice when we have an indeterminate product. But I like this example, but I probably wouldn't expect you to do it. Okay. If we don't have any questions, I think we do have a quiz to go over, right?